sell us the xenon. They're like, well, we're not going to buy this from you.
Yeah.
And xenon's really expensive, so.
Yeah, I mean, that's what I was helium. And helium's nowhere near as expensive as xenon, and it's still like insane. Okay, that was one thing. And then the other question, what was the other question? I had two.
Digital factor though.
Okay, well, if I remember all.
Turn to look that direction for a second.
Thank you. Oh, and also we have a video you want to see.
Oh, that's fun video. I didn't do it.
Is this Dust History?
It's like
paper bag.
you put a paper bag over the house.
Oh yeah.
Always fun.
Yeah, we're not gonna paint all chips off the ceiling or something.
Yeah. And they actually produce like a surprising amount of torque. We're at like what, 22? But like, you know,
roughly.
you say that, but then like when you feel it, it's like substantial.
Luckily, a paper bag gets up to a certain speed and it's got enough drag area that, it's high drag area, low mass, so it's very low ballistic ratio coefficient. So it's not like taking a bullet left in a gun around a movie set. Redistribution.
Yeah,
Body components.
that was an unfortunate observation. All right, well, thank you so much, Professor.
I did have a question on the sheet you passed out.
Yeah.
Like grade breakdown based on hours.
Okay, yeah. I'm using A, B, C, and D there because it's easy distribution. Your grade is not based on the number of hours you put in.
Okay.
The grade is based on the work you get produced. Yeah. And you guys are doing great.
Awesome. Yeah, I was like looking at that and I was like, this
is my classic way
track
of this is my way of scaring the crap out of people who are thinking that they can cruise until the last minute. It's like, we don't understand. An aircraft in a dive has a certain radius of curvature at which point wings fall off. And if your radius of curvature is larger than your altitude at the start of a power dive, you're going to die one way or the other. You're going to run into the ground, or you're going to pull too hard, pull your wings off, then you'll run into the ground.
Yeah. No, I figured that was the case, but just wanted to.
Yeah.
I remembered my question. I was going to ask.
Hello. Excuse me? I need to teach now. Sorry.
Oh, sorry.
All right. So, does it work? Okay. So last time, what we saw is the framework for computing, like for using the cut matching game for approximating expansion, right? And so just to recap, the framework, basically there are two ingredients. Well, it is based on like, it's a cut matching framework. So the two ingredients is obviously the cut player and the matching player. For the cut player, this is like some previous lecture ago. We have actually seen fast, randomized algorithm, and also not so fast, but deterministic algorithm. But actually, this can be made fast too. Like this kind of time is possible in the state of the art. And for the matching player, what is a matching player is a subroutine that either finds sparse cut or embed meshing. Right. Yeah. So, and this basically, how much time does it take?
Max flow.
Yeah, max flow. Yeah. Okay. So, and this is randomized, and this is time. Or it actually can be n. Yeah. Okay. So if you recall, like there are two graphs. One is your input graph, and another one is your expander that you want to embed into the graph. And the cut player only works on top of the expander, and the meshing player actually works on G. Right? So that's just a recap. Yeah. Okay, and so I mentioned that we show how to approximate expansion in the graph, but like we have seen that actually it can be extended to something more like conductance or even the expansion in general. Yeah. But this is not edge expansion for general graph edge actually. If you recall this, this is not the case. Yeah. And actually, we also saw that like you can just adjust the matching player a bit, and then you can get balance cut from it too. Do you recall, like, can you say a few words? Like, can someone tell me how did we adjust the matching player to get balance cut? Like the matching player compute max flow, and what did we change? Like in the computation of max flow. Yeah, like exactly. So in the unbalanced case, we just check if the size of the max flow is full or not. By full, it means like the size of max flow is like exactly A or less than A. But for the balanced case, like exactly A or less than A. But now we just ask, is it like bigger than A minus beta or less than A minus beta? That's how we did. Okay. So this is very flexible, but you see that all of this notion is really like still like kind of edge. There are just several kind of edge expansion in undirected graph. And this is a thing that kind of captured by the theory that we have seen in the first half of the class. Now, the point I want to make is that the cut matching framework actually is so flexible that it just works for all notion of expansion that like almost all, like not edge expansion, but almost all. Like if you want to compute vertex expansion, then you can do it too, or even directed graph or hypergraph, and you will see this in the homework. I try to guide it through. The point is just that if you want to compute, maybe can you try to guess, like if you want to measure a vertex expansion, how should we modify the matching player? Like the max flow instance that we create. How should we change it? Any guess?
For each and every vertex, we have to give 1 or 5 weight and then make that vertex in and vertex out.
Yeah.
And put 1 or 5 on that edge weight.
Right. Yeah. So exactly. So like we were trying to say that we can embed, like the meshing player will embed a meshing with it. We embed a meshing with this congestion, but this is edge congestion. And how did we get this edge congestion? Well, we just said that for every original edge in the graph, we put the capacity of edge to be 1/5. But now, it should be that like now if we want to measure vertex expansion, we just said that this max flow instance should have vertex capacity to be 1/5 instead of edge capacity. And with that, you will be able to embed, like we can define a notion of embedding with vertex congestion, just like we defined edge congestion before. And by doing something like this, you will be able to embed meshing with small vertex congestion. And if you can embed if you can embed an expander into a graph, and with small vertex congestion, then you are done. The graph will have a good vertex expansion.
I'll just make sure everything.
Okay, sure. Okay. Oh, what happened? Oh. Okay. One sec. All right. Okay. So the point is like, if you want to measure something on some notion of expansion, just adjust it to work it accordingly, then it will work. Like very flexible. And basically the total running time of any version of this is gonna be polylog many calls on MaxFlow in that version. Like if you want vertex expansion, it's MaxFlow with vertex capacity, like this. If you want to do it on hypergraph, you ask for running MaxFlow on hypergraph, and so on. If you want directed graph, MaxFlow on directed graph. Yeah. And and actually, what is even better than for this framework is that it is not really necessary that you need to compute exact max flow. So approximate max flow is enough, and I will guide it through in the homework as well. What is nice is that, okay, although the fastest exact max flow is not too slow now, it's like something like this, but the fastest approximate max flow right now is really near linear. So once you have this, then it means that like whenever like it's always about reducing the problem to approximate max flow, and if that setting you have like a nonlinear approximate max flow algorithm, then you can approximate the expansion in nonlinear time. Okay. And maybe I talk about this in the exercise session. Okay. Okay, now new topic, which is an important one, is expander decomposition. So you have seen like a rich theory around expander. Like they are great for so many reasons. And it makes us wonder, like, it would be wonderful if we can exploit expander somehow in the non-expander graph. That would be great, right? And the thing is that it turns out that we can in some sense. And this is where expander decomposition come into play. So today I will just define what it is and show you how to compute this thing fast. And next lecture is going to be applications of this thing. Okay. So what is expander decomposition? It's really just what happens when you keep finding sparse cut in the graph, like recursively. So let's be a bit more formal. What do I mean? And let's say in this lecture we were talking about unweighted graph and undirected too, just for simplicity. But you will see that everything is so flexible anyway. And let's fix the conductance phi as a parameter. Okay. Now let's look at this process, like the procedure decomposition. So if the graph is already in phi expander, you just return the whole vertex set. Okay. Otherwise, if there is some phi sparse cut, if it's not a phi expander, there is a phi sparse cut. Yes. So, which is sparse. Then what you do is that you just say you cut through, like you remove these edges along the sparse cut, and you just recurse the same process on two sides. Okay. And like, if you recurse on the same process, you might actually like find more sparse cut. You cut it, and you try to find more, and maybe you stop here, and so on. Like this is just really simple recursive iteration process. Okay. And at the end, you see that this procedure will return you like a partition of nodes, right? So like if this part return these two part, and maybe the other side return this part, it's just a partition of nodes into like, let's say, k parts. And you know that each part, it will induce an expander with parameter phi. So you get a bunch of expander. Now let's try to see a bit like how many edges we have cut throughout the whole process. How many like this purple thing are there? Okay. So let me denote this purple thing by partial of v up to vk. Like it's just this thing just denote all these edges crossing the parts. Okay. So we want to know how large of is this set. Now the answer is that it's going to be like something like phi times m times log m. So basically, like phi fraction of edges, roughly speaking. Okay. So why is that the case? Well, let's see. Like whenever we like suppose that you have a graph, and then you have a graph, and you find a sparse cut here. Maybe it's not balanced. It can be something like this. You know that these edges, the cut here, is going to be small compared to the volume here. Right. So what we will do is you just charge these cut edges 2 nodes on the smaller side. Okay. And how much for each node, how much would it be charged to? So you said that you put a charge of 5 times degree of u. You charge that much to u. And that is enough, right? Because the total charge is at most 5 times s. And like if each node in s is responsible for this much, then like you charge the whole set of edges here to this node. Okay. And now, how many times each node is charged? Well, it's gonna be just log m. And the reason is that, let's look from the perspective of node u. When it is charged, like it's on the smaller side of a cut. Every time you get charged, you are now working on the graph with small, like half size. So that can happen only like log m time, because every time you have the volume. Right. Okay. So with this, like, it means what? It means that the total thing that you cut, this thing, is gonna be at most, you sum over all nodes. And each node, you get this much degree of u. And each node, you can charge this much, log m. So this is like m log m, as we claim. So basically, this is what we get just from this simple procedure, right? Given any graph, there is a partition of vertices such that each part is an expander and like is a phi expander, and phi log m fraction, at most phi log n fraction of edges cross the partition. Every graph is like this. So this is something that you should keep in mind. Any graph is just a bunch of disjoint expander plus few fraction of crossing edges. Like every graph is a bunch of expander and few crossing edges. This is true for every graph. And this is why like the fact that like things are so great on expander, it seems that like if we have a tool on expander, many times you can really like just generalize the tool to every graph, because you just try to take care of an expander, and then there are just few fraction of edges left to take care of, and you try to take care of that somehow in a different way. So let's look at some example. Like this is just some example of a graph of expander decomposition, and I think it's something like look like this. Yeah, I should cite it, but if a graph is a path, okay. First of all, like this looks kind of natural graph it's like a natural graph clustering, right? Like you kind of discover something that looks like well connected and disconnect things out of it. Yeah. What if the graph is just the path? Well, you'll get some kind of simple partitioning. That is, it will return something like this. That is, you will cut through the path. And each part can have at most 1/5 nodes. Right? Because if you have a path which is longer than that, there is a sparse cut already. So basically, this is what you get in a path. What would you get if the graph is a star or a clique, actually? Can someone quickly tell me? Right, it's just the whole thing because it's already an expander. How about the grid? Like if a graph look like this.
Do we get root 5 blocks, root 5 cross root 5 blocks?
Yeah.
Root 1 over 5 cross root 1 over 5.
Yeah, it's gonna look something like that. Yeah. So basically, very good. Yeah. Like this is gonna be something like this much. Because if it is bigger than that, you will get sparse cut. So you get this kind of like it will decompose into something very small, basically. Just a function of phi and not function of n. So like a grid or like any planar graph, actually, this is what you're gonna get. Like there is no real large well-connected component in this kind of graph. You will find like the part that you end up with is just very small part. Yeah. An planar graph will be like this too, actually. But if there is some like a very well-connected part in that, then you will get that part as its own, like a big part. Okay. Okay, now this is simple, but you can see that the algorithm is slow, and this is for two different reasons. One is just that checking if there is a sparse cut or not is just NP hard. But this is like kind of simple to fix by now, I guess, because you can always use the approximation algorithm. And suppose that, let's say that the approximation algorithm either say that the graph is an expander, or find a cut such that is, let's say, phi times log square. So this can be done for sure, right? Then, and let's say this is alpha for approximation. If you keep doing this, what would you get here? Like, so it will be the case that this actually will be just multiplied by, by log square n, or which is alpha, right? It's gonna be the same, exactly the same reasoning, just because now when you find a sparse cut, this is now alpha times, like each cut will be alpha times this much. And the chart is just gonna be just increased by a factor of alpha. So that's now a polynomial time algorithm for you. But okay, it's still not nonlinear time. So because okay, suppose like we know that this thing actually can be solved like fast actually. Like I just claim that you can solve it using approximate max flow, and that is fast. like polylog approximate max flow. So that's nonlinear time. So even if this is solved, like this procedure is solved in nonlinear time, the whole expanded decomposition algorithm is still going to be, can be slow. And what's the problem?
For example, in planar graphs, we need like so many parts to be separated, right? So to enumerate them itself, it takes more.
That's not quite the reason yet. The thing, because if, let me tell you soon, but any more?
But so suppose the algorithm returns the whole graph, so we can see that the conductance of that whole graph is at least 5, right? So then we can use this algorithm to find the conductance, is it? Like if it returns the whole graph, then we know that the conductance is 5. So can we repeat it multiple times using different levels of 5? Can't we just do that?
You mean there is a chance that we can actually compute conductance? Actually, as long as we use this kind of subroutine for different value of phi, but as long as we have this gap, you will not be able to get things exactly.
So in the grid case, we first separated one block, then another again we separated one block. So you need to n 1 over 5 blocks.
Exactly.
For enumerating them, we need blocks.
Yeah, exactly. So like it can be the case that suppose we find a sparse cut and it's like it gives you these small blocks. And now you recurse on this whole thing. That is like the same. It's just the side, almost the same graph, and you maybe you get another cut, and you keep getting small cut, and you keep recursing on the big side of the graph, and that can like you can you might recurse on the bigger side O of n time. So even if this whole procedure is nonlinear, the total time is going to be at least mn. So not so fast. Okay. So now I'm gonna tell you that the thing can be fast. And you see already that okay, the bad case is when you keep getting unbalanced cut. And so it's quite very natural that okay, we should find balanced cut. And let's start by some definition. So let's say that given a graph G and parameter phi, we will define max balance. It's just the volume of the most balanced phi sparse cut. By which I mean that like it's maximum overall volume of the set among the sets such that it's phi sparse. And let's say that this set is also on the smaller side. Okay, so like if there are two, yeah, I guess you get the definition. Yeah. Okay. And if there is just no, if the graph is already a phi expander, so no phi sparse cut, define this thing to be 0. All right. And now we can actually show this algorithm, which let's call it balance cut phi G phi. So this algorithm either say that okay, it either return like nothing and say that there is no sparse cut, no phi sparse cut. So it report that. Okay. Otherwise, it returns some cut S. On S is on the smaller side. And S is phi sparse, but there are some factor like log square here. Okay. But the important thing is that it also promises that the volume of S is almost as balanced as max balance of max balance of a 5 sparse cut in G. So, but with some slack here too. So note that there is some gap here, right? Like phi, like S is phi log square sparse, but it compare the size of itself to phi sparse cut. Okay. And you can try to like use the content in the previous lecture and say that you can actually solve this. It's just do some binary search using this balance cut algorithm in the previous lecture. Yeah, do binary search on beta basically. Okay. All right, so I will just assume that we can solve this thing, right? When like the approximation on expansion and approximation of balance is something like log square. Okay. So yeah, you can try to say that to show that you can use cut matching framework and take like polylog, even approximate max flow, or polylog max flow. You can solve it. And now the natural way to use balance cut in the decomposition algorithm is just this thing. So let's say that you given any graph H, you compute balance cut in it. And if there is no sparse cut, just return the whole thing like before. Otherwise, okay, this should be phi h s. Otherwise, there is a sparse cut of this conductance. Then you recurse on the both sides. Okay. And you just call this thing. And that's the algorithm. Okay. So this looks very natural, right? Like you keep finding sparse cut, just like before, but now the cut that you try to find, you say that it should be most balanced one. Okay.
What is phi h?
Phi h of s?
Phi h of yes. Oh.
Phi h of s, yeah. Just the conductance of s in h. Okay. Okay. So this looks very natural, but it's not going to be the final algorithm yet. Okay. But let me at least like try to tell you why it looks good. So let's look at the lucky case. That is, suppose somehow that this balance cut algorithm really return you a balance cut. That is like the both sides of a cut is balanced basically. Note that this might not happen, right? Because it can be the case that like even the most balanced phi sparse cut might not be so balanced. That can happen. Even the most balanced one is like kind of skew. Okay. That can happen, but suppose that suppose somehow that okay, this guy really returned you a balanced one. Then the total running time is going to be good now. Why is that? Because if every time you have this kind of cut, when you recurse on both sides, the volume is gonna drop by a constant factor, like 9/10 factor. So the recursion depth will be log m, right? And now, once you have that, okay, let's draw some recursion tree. So this is a graph on GS, G on, and so on. and so on. We have that all the graphs on the same level are disjoint. So the total size of this is linear. Yeah. The total size of one level is linear. And if you have nonlinear time algorithm and run it on every graph here, it's going to be nonlinear. But there are like just log n level of this tree. So the total running time is just log n times the total time on each level, which is nonlinear in total. Okay. So if you get this lucky, if you are in this case, then things are good. Yeah.
Looks like the cut matching game. First we try to find balance cuts and then otherwise we do something else in the last step.
Yeah.
Something similar to that.
Yeah. So let's see. Yeah, I think like the final algorithm gonna have that flavor. Yeah. Right. Okay. Okay, so this is a lucky case, but yeah, I just told you that like it might not be it might be possible that we cannot be lucky just because all 5 sparse cut turns out to be not balanced. Like there are like a lot of there are 5 sparse cut, but they are skew like this. So this guy cannot, and let's say that even not just all 5 sparse cut, but all 5 times this thing. Even 5 times Cx sparse cut are not balanced. Then this guy cannot return balanced cut, right? Because the cut returned by this guy is return 5 times sparse cut. Yeah. So suppose that all of these cuts are not balanced. Yeah. So then does it mean that like you might get like small cut and you might need to repeat many times? Well, this somehow like intuitively this shouldn't happen because intuitively your algorithm say that you try to find most balanced one, and if you keep finding small sparse cut many times, yeah, so that shouldn't happen. Exactly, like this union seems like it contradicts the fact that you are trying to like you find the most balanced one. This intuition really is captured in this ideal setting. So the ideal setting is that suppose that you get an exact algorithm. That is, suppose somehow magically you can solve this one when there is no approximation. Okay. And let's say you can solve it in linear time. Okay. And then, so let's say that S is the most balanced sparse cut, most balanced 5 sparse cut. So because there is no approximation, we really have that volume of S is this thing, and S is 5 sparse. So it's just the most balanced cut among all sparse cut. Okay. So suppose that S is not balanced. Suppose this is S. Even if it's the most balanced one, it's not sparse. It's not balanced. So S is small. Now let's look at what we get when we recurse on the bigger side. We recurse on this bigger side. And let's say that we get S prime. Okay. Yeah. So S cannot be like, can S prime not balance again? Yeah. The intuition that we have is to say that no, and this is in this case. So let's be formal. Why is that? Like, because you have that S is phi sparse in this graph. So this is phi sparse. And S prime is phi sparse here. You don't even count this thing, right? You just count, you really just count this thing, not this. And so this union is going to be phi sparse cut in G, because if you look at the union, you just count this part. So we actually have that even if you count this thing too, like the total size of the cut on the green thing and the blue thing is small compared to the volume of the union. And so like if you just look at the cut and look at only green thing, this green thing is going to be small compared to the volume too. Okay. So you get that this thing is a phi sparse cut, but this thing is bigger than S. So we say that S is the most balanced phi sparse cut in G, but S union S prime is a phi sparse cut too, but it's bigger than S. So that is contradiction. So what does it say here? It means that we cannot get very unbalanced cut 2 consecutive times on the bigger side, right? If you get an unbalanced cut first for once, next time you will get a balanced cut. And once you have that, it means that the recursion depth is going to be log m, right? Because instead of saying that you have every single, like the cut size, the graph size reduced by a constant factor every time, now you just say that for every 2 steps, it reduced by a constant factor. So the recursion depth is log m again.
Why the next time we can get balance cut?
Say it again.
Why the next time we can get a balance cut? Because if S and S prime, the union of them is cut bigger than S. So it seems that it contradicts the character.
Yeah, so it said that like it cannot be the case that both S and S prime are unbalanced.
But even if S prime is balanced, it still contradicts the character.
Oh, so yeah, this is just a corner case, which is just a bit annoying. That is, if S is here and S prime is here, and the total size here is already bigger than half. So yeah, it's just like annoying corner case. Yeah. Okay. So like morally, it should be the case that once you get a cut which is most balanced, you shouldn't even find any sparse cut at all on the bigger side. But because of this annoying case, you just say that, okay, you cannot find unbalanced cut on the bigger side twice. Okay, so, but this is a good intuition, like getting most balanced cut seems like it should really reduce the recursion depth, right? Because you shouldn't find balanced cut, like sparse cut many times on the bigger side. But you see that things actually goes wrong already if you just allow some approximation on the expansion. Let's say the approximation on the expansion is even 2, not even like log square, just 2. This argument still goes wrong. And we just need to look at the picture. So these now are like 2 sparse cut, 2 phi sparse cut. Okay, so it's true that this union is a 2 phi sparse, but it's a 2 phi sparse cut, which is bigger than S. But like now there is no contradiction, right? Because S is promised to be the most balanced phi sparse cut. Now we get a bigger cut, but this is just 2 phi sparse. It's not phi sparse. Is this clear? Like this is no contradiction. Like it's not sparse enough. This guy is not sparse enough to get a contradiction. Yeah, so then it would be contradiction, but what we like when we call this algorithm, right? Where is it? When we call this algorithm, we really just say that this thing is bigger than this phi, like than the most balanced phi sparse cut. But S itself is not phi sparse. Right. Yeah, so this is like a technical problem that makes us like you don't get the contradiction that you want. Yeah. So, and actually it seems like if you really just run the algorithm as we describe here, that is we literally just where
Should we put C balance as 2 as?
Sorry. Say it again.
Should we put C balance as 2 as well?
Oh, that wouldn't help because so even C balance is 2 or whatever. S and S prime is going to be 2 sparse cut, 2 phi sparse. Like C balance doesn't change the fact that S and S prime are 2 phi sparse, but we want to really like compare this cut to a phi sparse cut. Yeah. So if we really just run this algorithm where you find sparse cut and recurse immediately on 2 sides, it seems like because of this problem, you might actually get high recursion depth, like n still. Because you really just, okay, you keep getting like phi log square sparse cut, and again and again and again and again and again. And this in total like yield no contradiction. Okay, so now is the trick. It's a cute trick, but it makes everything work. Like, so in reality we have this parameter which is like not even a constant, it's log square. But let's see, right? Let's see how bad it can be. Like, so okay, let's look at the case where it seems like super bad. So you get a cut S, which is super unbalanced. Like, let's say that the volume is a constant. This looks like the worst thing ever that can happen. Okay, so actually S might not be useful, actually. But we know that here, the algorithm said that, okay, the max balance, okay. The algorithms actually say something strong in this bad case. That is, it says that the maximum balance of 5 sparse cut is going to be like O of 1 times C bar. So most balanced 5 sparse cut is going to be like log square big at most. So this information seems useful to us already. Like, at least we know that, okay, 5 sparse cut is going to be small. So now comes the key trick. Well, what if we just say that from now, just use this information as it's given to us that this thing is small. And just now, you just call balance sparse cut with this parameter. Okay. Instead of 5, you take like 5 over log square into the parameter. Which means what? It means that the cut that is returned by this procedure must have conductance at most this parameter times this, which is 5. Yeah. And now the cut that is returned by this procedure with adjust parameter, you now get 5 sparse cut, and you can compare the cut here with the guarantee from before, which is about 5 sparse cut. Just adjust this parameter so that things match up. Okay, so now can like once you use this parameter, can you keep getting very small cut like of, let's say, constant volume on the bigger side many times? Then now that cannot happen, because if like not more than like C bar times at least, because otherwise now the union of that is gonna be 5 sparse cut, right? So okay, think like this. You start with S here. This is like a log square sparse cut, but you really don't use this thing at all. You forget about this black information, and you just use this promise about this thing that 5 sparse cut is small, and now you call balance sparse cut in this with this parameter, and maybe you keep getting sparse. Now this is 5 sparse cut, and if you keep getting this thing, many of them, now the union of this guy is 5 sparse cut too, and this just cannot be bigger than the red thing. So you cannot just call, you cannot find green cut many times. That cannot happen. Okay, so that's really the idea. Now we are ready to present the whole algorithm. So, okay. So let's set epsilon to be like 0.01, small constant. You can think about it that way. But at the end, it's going to be a bit smaller than a constant, actually. Okay. And L think of it as some upper bound of level in some sense, and L is going to be 1 over epsilon. And now this is a part where we have, like, we said before that adjusting the parameter is good. So now we will actually have parameter to adjust for many levels, actually. So we start with phi 1 up to phi L plus 1. The last phi L plus 1 is going to be our phi. Like, we want a phi, like, decomposition of a phi expander. This is our phi here. So, like, each of these, like phi L minus L, phi L plus 1 is phi L over this thing. So, like, yeah, phi 1 is the biggest. And it's going to be like, when this is like log square n, basically this is log square times Ln. Like phi 1 is like, is phi times polylog. Okay. Okay. And below I'm gonna use m as some fixed parameter. So note that our algorithm is recursive, right? Like it's gonna be a recursive algorithm, but m here is gonna be a global variable that I fix. It's just the number of edges in the original graph. Okay. So now this is the algorithm. So when you call H and level L, what you do is similar to before. You call this thing. You find balance cut on H, which is with this parameter at phi L plus 1. So think like this. If you are at level L, you are looking at kind of phi L sparse cut, and that's why you set this parameter to be phi L over this thing. Just like we did before, like we actually call this, the parameter here is should be this thing over the approximation, so that the cut that is returned by bar cut is going to be phi L sparse cut, not just like, it's not phi L times some approximation, it's phi L sparse cut. Right. Okay, so you call this S is like balance cut with this parameter. Okay. And if S is empty, it means that this algorithm report that the whole graph is phi L plus 1 expander. Then you just return the whole thing as your part. Okay. So otherwise you get that, like from like here I just write down the promise of balance cut algorithm, right? It just means that this S is this sparse, which is phi L exactly, and the cut size, the volume of S is as big as phi L plus 1 balance cut over some factor. Yeah. Okay. So this is just the promise of the algorithm, right? Of balance cut, the promise of balance cut. Okay. So if it is just the previous case, what we would do is just, once we get sparse cut, just recurse on both sides, and that's it. And now we're gonna actually have two cases. If S is kind of already balanced, if it is balanced in some parameter here, like you don't need to understand this now, but it means S is quite balanced, then it makes sense to recurse on both sides. Otherwise, if it is not balanced, if this volume S is small, what we just do what we just described. We just adjust, like just use that knowledge that now, okay, S is small, so S is not so useful, but you know now that the max balance thing is small, and so you can just adjust the parameter. And by adjusting parameter here, I just really just call the same algorithm and increase the level. This is what I mean. This is the same thing as adjusting the parameter, like by like CX factor, right? So, question about the description of the algorithm, like, and now when you call it, like when you want to decompose a G, you just call G on level 1. That's the algorithm.
Phi log 2L n is should be less than 1 another, right?
This, you mean this thing?
Yeah.
Well, this thing, if L is like, if epsilon is constant, then L is a constant, then this is really just polylog. What's your question again, actually?
Yeah, I want that the pi, that quantity should be less than 1, right?
Phi is less than 1 for sure.
Phi is less than 1, but phi into...
Oh, yeah, right. Yeah, phi, like this whole thing should be less than 1. Otherwise, you cannot, like there is just no sparse cut like that, yeah. So you should think of phi as, like this parameter phi should be like, think of it as maybe a 1 over polylog or like 1 over n the little 1, thing like that, yeah. Okay. So that's the algorithm description. And so the difference between the straightforward one and this one is that this one has level. And when you recurse, now it depends whether the cut S is balanced or not. If balanced, you recurse on both sides. Otherwise, you adjust parameter. Okay. Now let's look a bit more into how we recurse. When the cut is balanced, I recurse on both sides. And actually, on the smaller side, I call it left recursion. Like at the end, I would draw some recursion tree. And this is like small side. The left side is always like for small part. The right side is a big part. And on the left side, actually, I will restart the level to 1. On the right side, the level stay the same. And otherwise, when I adjust parameter, I call it down recursion because it's really just like the same graph. I just look at the same graph with this level increment. Okay. So now let's analyze it. Okay. So again, it's enough to analyze the depth of the recursion. So if the recursion is D, then what's gonna be running time? Total running time?
O tilde MD.
Yeah, O tilde MD, because just use the same argument, like every graph on the same level are disjoint, and total time is nonlinear. So we just need to analyze the depth now. So let's consider the recursion tree T. And there are like, each edge is gonna label left or right or down. Okay. Left is for smaller side, right is for big side, down is for same graph, but you increment the level. Okay. And if you look at the recursion tree and like take the leaf, the node X as your leaf, then this leaf will correspond to an expander, right? Because that's only when you stop your recursion. You stop your recursion when you just, when the algorithm say that is it an expander? Okay. So now let's take one path. One path from root to leaf, call it P. The first thing is that P can contain at most log m left edges. And that is kind of easy to see. The reason is just that, like when we go left, we halve the size. So that cannot happen more than log m time. And now, the next thing is, if I look at the path P, and let's say that there are some left and left here, and let's look at the path between these consecutive two left edges. Then I claim that there can be, this is the left. There can be only like L many down edge here. Like there can be, between here there can be like down or right? I claim that there can be at most L many down edges. So why is that? If you look at between any two consecutive left edges, the level never decrease. This is just by the way we do it. Like we either like keep the same level for right or increment the level for down. Okay. So if there are L down edges, then the level must be like at least L plus 1. Like it actually starts from level 1. And if there are L many down, then the level is L plus 1. But let's look at this condition. The condition here, okay. So when L is like L plus 1, or actually when L is even just L, this condition can be written as whether volume, like if this volume is at least something less than 1, something at most like something less than 1. So this condition gonna be true no matter what. Like if as long as S is some non-empty set, you will get that this is true, right? So it means that you will not go to this. You cannot increase the level again. So this is why there can be like L down edges. Okay. Like the basically after after level L, when L is like a capital L plus 1, this condition about balancedness is kind of trivial. You always like recurse on both sides. You never go down. Okay. So this is what we get now. So now you have that in each path there can be log n left edges, and between any two left edges, you bound the number of down edges. Now it remains to say that, okay, between any left or down edges in the path, you want to bound the number of right edges. Right? So if you can do that, then you can like if there are at most between any left or down edges, there are at most r right edges, then what would be the total length of P? It's gonna be at most like log M times L times R. Yeah. Right. Because you really just, yeah, I will not prove this. I think, yeah, it is fine. So, but there are like just three labels, either left, down, or right. This is the same thing. Like if I want to prove that between any these two, there are at most r many right edges, it's just the same thing as saying that there cannot be like r consecutive right edges in the path. Okay. So that's what we want to prove. Like we want to bound R. And now observe that the algorithm maintains this invariant. So if we call the algorithm at level L, if you call it at level L, then I claim that the maximum balance of phi L sparse cut is going to be this much. Like whenever you go to level L, you know that the cut must be quite more and more unbalanced. And this is true for like for L is 1, this is trivial because this is just M, right? And any cut on the smaller side have volume at most this much, which is M. So this is just trivial. But how about other L? Well, you know that L is increment only by down edges. Okay. So before, and let's look at what happened before L is increased. So let's look at the moment when you call this thing, all right? You have that, to call this thing, you have that the volume of S here is less than this thing. Okay, this is what you know. But you also know that this volume S is bigger than this thing. So you compare the two things. And it means that this must be less than this. So just before L is increased, you have this thing and this thing. So you just look at, you have this thing. And now once, one sec. Oh, forget this. This is something that I should delete. Yeah. So you have that this thing is less than this thing, and then you increment L by 1, and that's how you get this exactly. Right. This thing is just now like replaced by, this is replaced by L. This is now replaced by L minus 1. Okay. So the point is just when you go to level L, you know that the max balance cut is kind of more and more more and more skewed. Okay. Okay, now I can prove that there are, now we're gonna bound the total number of right. Okay, so let's say that this is a path P in the recursion tree, and let's look at P prime, which is like everything here is right. Everything in P prime is just the right edges. And let's say that the first graph here is H1, each node here corresponds to one graph, right? So the first one is H1, H2, and so on. This is like HR plus 1. And the algorithm basically call this thing. Like when you look at this the call of the algorithm in the recursion, you have this. Like that it call things at the same level. Right? It must be the same level because when you go right, you don't change the level. So this is like all the same level. Okay. And just from the invariant before that we claim, we have that when you call it at H1, you have that the max balance cut at H1 is this big. Okay, so now it's the same picture. You have that in H1, the opt, the max balance is this big. Okay. And now just look at each SI, the sparse cut that you get. The sparse cut that you get for each in each call in HI. Each of them, we design it in such a way that they are all phi L sparse. And the fact that we go on both sides, on the left and the right, you know that this cut is also quite balanced. It's not as balanced, as this is not like this is L minus 1 here. So this guy, S is like just M over, this is SI. Okay. So each of SI is this big, not as big as the red thing, but close. And so if you find if you find many SI here, like if R is big, then the union of them gonna contradict this thing. Right. So that's the idea. Like I claim that look at the union of this, then this is gonna be phi L sparse because each of them are phi L sparse. Okay. So this is gonna be true actually if this total, the union of this whole thing is not more than half. Okay. And but it might not actually be true if this is not the case. But it should be true, and you think of it as an exercise how to handle that if this is not the case. If this is not the case, actually it's gonna be good case, right? Because you get like balance cut. But anyway, you have this, and if this total thing is phi L sparse, then the total volume of this union is gonna be contradiction. So that's how you bound the right edges. And now you have that the total length of any path is small, like this big, which is something like m to the epsilon.